You built the index, but your query still scans thousands of rows. Why? Because index column order dictates usability. A composite index on state followed by city is useless if your query filters only by city. The database engine relies strictly on the leftmost prefix rule. If the query predicate skips the first column, the index becomes a partial scan, or worse, a full table scan disguised as an index lookup. We are talking about milliseconds versus seconds in high-volume transactional systems. Understanding this prefix dependency is the single most critical factor in optimizing complex database queries. Ignoring order means the index structure you paid for is only partially utilized, forcing unnecessary input-output operations. The leftmost prefix rule, or LPR, states that a composite index can only be utilized if the query includes the first column, or a contiguous set of columns starting from the left. For an index defined as A, B, C, the engine can efficiently use A and B, or A, B, and C. It cannot use B, C, A and C, or B and C for direct seeking. If the query uses B and C, the engine must still scan the entire index structure, filtering the results based on B and C, which defeats the purpose of the index seek operation. This is fundamental. The index structure is a sorted tree based on the concatenation of the column values in the defined order. Breaking the prefix chain forces the optimizer into less efficient access methods. When all predicates are equality checks, like where department ID equals 5 and employee status equals active, the order matters primarily for selectivity. If department ID has only 5 distinct values, but employee status has only 2, placing the higher cardinality column first, department ID, generally reduces the initial search space faster. However, if both columns are used with equals operators, the index can seek directly to the starting point defined by the combined key. The engine performs a single seek operation to find the first matching row, then scans until the combined key changes. The key takeaway here is that equality predicates maximize the index usage depth, allowing the engine to utilize every column in the index prefix for seeking. Range conditions immediately halt the index's ability to perform further seeking on subsequent columns. Consider an index on region, sales date, and product ID. If the query is where region equals West, and sales date between January 1st and January 31st, and product ID equals 100, the engine seeks efficiently on region. It then performs a range scan across sales date. Once the range scan begins, the index structure for product ID is no longer sorted relative to the overall query result set. Product ID can only be used for filtering the rows retrieved by the range scan, not for further index seeking. Therefore, range columns should typically be placed after all equality columns, but before any columns used only for filtering or sorting. Cardinality is the number of unique values in a column. Selectivity is the ratio of unique values to the total number of rows. High cardinality is often desirable for the leading index column because it quickly narrows the search space. For example, a user ID column is highly selective. A gender column is low cardinality and low selectivity. When designing the index order, prioritize the column that eliminates the largest percentage of rows first. If column A filters out 90% of the table and column B filters out 50% of the remainder, A must precede B, regardless of their raw cardinality counts. Always use selectivity estimates from the database statistics to guide your column ordering decisions.
If your query includes an order by clause, the index column order must match the sort order exactly to avoid expensive in-memory sorting operations. If the index is last name, first name ascending, and the query is order by last name descending, first name ascending, the index cannot be used for sorting. Furthermore, if the index is used for seeking based on where predicates, the order by columns must follow the seek columns contiguously. If the index is A, B, C, and the query seeks on A, the engine can use B and C for sorting. If the query seeks on A and C, but not B, the index cannot satisfy the sort order efficiently because B breaks the continuity required for the sort operation. System analysts often face multiple critical queries hitting the same table. Index design must prioritize the most frequent or most performance-sensitive query patterns. If query 1 uses A and B, and query 2 uses A and C, a single index on A, B, C, or ACB might cover both, provided A is the common leading column. If query 3 uses only B, a separate index on B is required, as the composite index cannot satisfy the LPR for B alone. Always analyze the query execution plans for the top 5 most resource-intensive queries to determine the optimal shared prefix. A single, well-designed composite index is usually superior to multiple overlapping single-column indexes. A covering index includes all columns required by the query, both in the where clause and the select list. This eliminates the need for a costly bookmark lookup back to the base table. When designing a composite index, place the columns needed for seeking, the where clause, first, adhering to LPR and selectivity rules. Then append the columns needed only for projection, the select list, as included columns if the database supports them. Included columns do not affect the index structure sort order, but ensure the index is fully covering, drastically reducing input-output operations. This technique is essential for optimizing reporting queries that retrieve many columns. Theoretical index design is useless without validation. Use the database's execution plan tool, such as Explain Plan in PostgreSQL or SQL Server Management Studio's execution plan feature. Look specifically for index seek operations versus index scan or table scan. An index seek confirms the engine is using the index efficiently based on the prefix. If the plan shows a residual predicate or a key lookup, the index is either not ordered correctly or is not covering the required columns. Iteratively adjust the column order and rerun the plan analysis until the most efficient seek path is achieved. Never deploy an index without verifying its usage pattern in the execution plan. To summarize index ordering, Rule 1. Always satisfy the leftmost prefix rule for your most critical queries. Rule 2. Place equality predicates before range predicates and range predicates before columns used only for sorting or covering. Rule 3. Prioritize columns with the highest selectivity first among the equality predicates to minimize the initial search space. Adhering to these 3 rules transforms slow queries into sub-millisecond operations, ensuring your application scales efficiently under heavy load. Proper composite index design is the difference between a scalable system and one that collapses under peak traffic.